Sure, that's okay. How are we doing? All ready for the test?
Yes.
All right, so let's talk about test stuff. Ben, are you still coming in tomorrow at 10?
Yeah, does that work?
Yeah, that should be fine. Do you know who Ginger our time is? The worst? Yeah. I'll give her to the test so she can just give it to you.
Okay.
Yep. Yep. I won't be here at 10 because I have a dentist appointment, so I know for a fact I won't be here at 10. Just let me know when you're going to be in to take it, and that's fine. Doesn't matter to me when you do it. Just let me know. So, all right. So let's talk about test type of things. So, of course, you need to remember central limit theorem. What did that say again?
We can use normal approximations. We have a lot of sample.
Right. So the distribution of the sample means, or of the sum of x's as well. But the distribution of the sample means is approximately normal. If n is little n is large enough. Usually by large enough, of course, we mean greater than 30, which if you've noticed in your t-tables, that's as high as it goes, right? And it goes infinity past that. So the actual formal statement is that if you take the sum of your x sub i's and subtract off n times the mean of the x's, so your x sub i's are representing a random sample from the distribution of x. If I'm doing a random sample, of course, they're all independent. The mean of each, if I think of them as separate distributions, all should have the same mean as x because you're drawing them all from x. So the mean of that entire distribution should be n times the mean. And if you divide it by sigma times the square root of n, that's the square root of the variance, right? Remember when you have independent random variables, you add the variances? So the variance of the sum of the x sub I should be n times the variance of the x. I'll put a sub x here, just to emphasize that. So you're dividing by the square root of the square root of the variance. So you're dividing by the standard deviation. What we've done here is standardize this, right? So this approaches a standard normal distribution as n goes to infinity. It's a limiting distribution. If that fraction is, I think, the formal statement of the central limit theorem. But if we divide top and bottom by n, I get the more familiar form of, I get the 1 over m times the sum of the x's, that's the mean, minus the mean of the population, over sigma over the square root of n. You get your more formal, or your more familiar statement involving sample means. Whoops, where'd it go? That was weird. I don't know why it keeps pausing. Anyway, sorry. One of the best things about watching these videos is me giving editorial comments. All right. That sound familiar? That part? Okay. So what else did we talk about? We talked about the distribution of different types of variables as well. We know that, and this is in part of this is in the central limit theorem as well, but we know that if your x sub 1, x sub 2, out to x of n are normal random variables, then the sum is also normal, right? So sum of normals is normal. And we just talked a minute ago that as long as they're independent, well, independent or not, we do the sum of the random variables. The mean of the sum is just the sum of the means. As long as they're independent, the variance of the sum is the sum of the variances. Right? We just talked about that a little bit ago. What if there are standard normals what is the distribution of the sum of the squares? Again, I know I didn't write it down, but I'm assuming things are independent here. Now, yeah, it's chi squared on how many degrees of freedom? 10. Good. When we square a standard normal, we get a chi-square on 1 degree of freedom. When we add chi-squares, we get a chi-square, and it adds the degrees of freedom. So when you square standard normals and add n of them together, you're going to get chi-squared of n. Okay. I'm just going through different distributions that we talked about. So if we have our sample variance s squared and multiply it by n minus 1 and divide it by the variance of the population, what kind of random variable is that? And that's also chi-squared, and it's n minus 1 degrees of freedom. Good. So again, your s squared is your sample variance. Your n minus 1 then is your n is how many items are in your sample. Sigma is representing the population standard deviation, so sigma squared is the population variance. We get a chi-squared random variable. We also used that to figure out confidence intervals for variances, right? Going to the chi-squared table. Okay.
Do we need to recall the sort of handling we did in class?
For
this thing?
No. 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 Yeah, you don't have to worry about the proof of that one. The hand wavy part of that was the fact that the sample means and the sample variance are actually independent. That was the big handy wavy part that we're going to do later. Because we rewrote it as a couple of, we wrote it as a sum of a couple of chi-squared things. That was how we got to it.
It was chi-squared, and on the other side we had j denominator squared.
Right. Yeah. Right. Exactly. And it was the fact that we were able to, the fact that the sample mean and the sample standard or the sample variance are actually independent random variables is what let us get to that, to be able to do it that way. Yep. All right. Lost my train of thought. That's all right. Talk about a different. I'll get back to it, I'm sure. When we had small samples, we had to do the t distribution. Remember how a t distribution is defined? It's a ratio of two distributions. What two types of distributions have to be in the fraction to get a t? There's a standard normal on top, right? I'll call it z, so make sure think about it as standard normal. And on bottom, yep, it's a chi with r degrees of freedom, and I have to do square root of that, right? So your Z is normal 0, 1, and why do we keep jumping everywhere? And U is chi-square on R degrees of freedom. So as an example of what I mean by this, say I asked you, let's say I defined a random variable, and I'll just call it T. You can back up to the x1 to xn. Just assume that we've got that random distribution, random sample from standard normal distribution. So same setup as this part here, right here. Same setup as that. Let's say our T is, let's say x1 squared plus x2. Let's say we do x1 plus x2 plus x3 over square root of x4 squared plus x5 squared plus x6 squared plus x7 squared. And so I asked you to find C so that C times T is a T distribution. Basically, these types of questions are just playing around with the different types of distribution, making sure you have at least a fundamental understanding of what's going on in each type of distribution. Okay? So to make it T, what has to be true about on top? It has to be standard normal, right? Right now, I took the sum of normal distributions, and we know that sums of normals are normal, right? And in this case, the mean is not going to change because the mean of all of them are 0, right? But what's the variance going to end up on top? 3, right? Right, so the top here, the x1 plus x2 plus x3.
Each exercise is standard normal.
Say that again?
Each exercise is standard normal.
Yeah, each one's standard normal. Yeah, I want the same setup as that, what I underlined there.
Oh, okay.
Yeah, I want it to be the same setup. Otherwise, it's not very interesting. Otherwise, it's just harder.
Yeah.
I would have to subtract something off. At worst, I want the mean to be 0 because I don't want to have to mess with the mean. I just want a constant multiple here to illustrate what I'm talking about. All right, so the x1, x2, x3 is normal 0, 3, not normal 0, 1, right? So what would I need to multiply or divide the top by to make it normal 0, 1? Probably something involved with the 3. Is it just straight up 3? It's square root of 3, right? Because remember that when we standardize, we take variable minus mean and divide by the standard deviation, not the variance, right? Right. So I need to take this x1 plus x2 plus x3 and then divide by square root of 3 is normal is 0, 1. Right? So I know that 1 over square root of 3 is going to be involved in my C somewhere, right? We agree? All right. Now I need to look at the bottom. I want to make this a T distribution. So in the denominator of a T distribution, we need a square root of what type of variable? Chi-square. And then we have to divide that by the 4, in this case, the degrees of freedom for the chi-squared, right? So we look at this, we know that x4 squared plus x5 squared plus x6 squared plus x7 squared is chi-square of 4, right? We agree? Okay. So going back over here, we started with, I'm just going to rewrite my random variable. The only problem with recording these is I have to scroll so much and go back. All right, this is what we started, right? You told me that I needed to put a square root of 3 there, right? I'm also going to need to put in a square root of 4 on bottom, right? I agree with that? To make it work. So if we pull out the constant so that I have c times t, this is what, 2 over root 3t? Because I'm just looking up, because I just want to multiply it by the c. Yeah, I wasn't trying to keep it equal. That would be a reverse question. That would be saying t is root 3 over 2 times a t distribution. This one I was just literally looking for what is the c do I need to multiply by to make it work. Yeah.
Yes. T equals root 3 by 2 times that.
Yeah. Yeah. So this would be my c then. Does that make sense? You okay with that?
So, in what circumstances did we use t for?
The t distribution is one we use for the small sample size where the variance is unknown. And then also used it for if we had small sample sizes for differences of means, again, where the variances are unknown but assumed to be equal. I was going to go through that too. I'm going to write those down as well. We also talked about, am I on number 5? Yep. We also talked about F distribution. That was one of the more recent things we did for ratio of variances. What has to be on top and what has to be on bottom? If we're going to do ratio of variances, and we know the sample variance has what type of distribution typically? There you go, yeah. That F table is that huge table in the back, because you have to have degrees of freedom for the numerator and degrees of freedom for the denominator, and then varying significance levels. So lots of fun. Those are the main types of distributions of random variables that we've talked about this semester. Of course, we had other types of distributions last semester, but these are the main ones that we talked about that we've been using for confidence intervals, right? Normal and t and chi-square and f. So again, much like I talked about that previous one, I could say as an example, if I'll call it f for lack of a better letter, if you've got x squared, say x1 squared plus x2 squared plus x3 squared over x4 squared plus x5 squared, x6 squared, x7 squared, x8 squared. Again, let's find a c to make an f distribution. What do I need to multiply this capital F by to be an f distribution? 4? I think I wrote 5, didn't I, Bob? Yeah, so in the numerator we need to divide it by 3, right? And in the denominator we need to divide it by 5. So if I do 5/3, oops, that'll get me what I need. Because I need to do a divide 3 here and a divide 5 here, right? Does that make sense? What else did we talk about? Well, we talked about, I'll get to the confidence intervals here in a sec, but I also want to remember that we talked about point estimates, and with point estimates we talked about maximum likelihood estimators. I can spell the word likelihood. Remember what we did? It's interesting recording with pausing all over the place. I don't know why it keeps doing that. Anyway, see what happens. Remember your maximum likelihood estimators are where we took the likelihood function of whatever the parameter is, right? The likelihood function is the product of your PDF evaluated at some sample that's in terms of the parameter theta. And then we wanted to maximize that function. So to maximize, of course, we have to take a derivative, set it equal to 0, and all that good stuff, right? To help us out, we typically did the log likelihood, right? Because it changes this into a sum of logarithms. Remember doing those problems? Okay. So then we differentiate with respect to theta, set equal to 0, and solve. That's how we did that, right? So you might be asked in a problem, well, you'll probably be pretty much guaranteed that you're going to have to find a maximum likelihood estimator. We spent a good time on it, right? But you might be asked to find the maximum likelihood estimator, figure out what that is, and then use a sample to give an estimate for that estimator. You did ones like that, did ones like that in the homework, right? We also did method of moments. So remember, the idea behind method of moments is literally to set your theoretical moments, you set them equal to the calculated moments from your sample. And you do that for as many times as you need to get the system of equations that you need. So if you only have one parameter, then it makes it pretty easy. You just set the mean with respect to the parameter equal to the mean of the sample. Right? Right? So, but if you've got more than one parameter, maybe you have two parameters, and you would set the mean equal to the mean of the sample. You set the variance plus the mean squared equal to the expectation of the x squareds. Right? So, as an example, if you had, say, x is gamma of alpha theta, then you would set your mean, which is alpha theta, equal to 1 over n times the sum of your x's. That's your calculated first moment, right? This is your theoretical first moment. But if you need to solve for both of them, then you would do what? Alpha theta squared plus alpha theta quantity squared. Variance plus square of the mean to get you your theoretical second moment, right? And that would equal 1 over n sum of the x squareds. Okay? That's what I mean by doing theoretical moment equaling calculated moment. And in this case, we would do two equations because we have two unknowns. Now, we could simplify things a bit. Say you were told that one of the parameters was known. So if I knew, say, theta, then I wouldn't need the second equation because I can just divide through by the theta that I know and figure out what my estimator for alpha is. Right? So that would give you a method of moments estimator by just ignoring the second equation and only worrying about the first. Does that make sense? So if I knew one of the parameters, I could figure out this other parameter using method of moments quickly. I wouldn't have to have two equations, I just need one. Because I only have one variable that I need to solve for. Does that make sense, what I'm saying? You wouldn't have to do the two equations with two unknowns because I know one of them. So in this case, if you knew either alpha or theta, the other one would just be the sample mean divided by that parameter that you know.
So calculator moments are just, say, if I calculate moments with e to the power xn, it's just sum of all xn's divided by n?
Yep.
Okay.
Yep. Yeah. This one? This one is the variance. So this is plus the mean squared. That's expected value of x squared. Right? Yep. All right. So those were the two types of point estimation we did, right? We did maximum likelihood estimation and we did method of moments estimation. Then we started to do interval estimation. So our confidence intervals, if your variance is known, then your confidence interval holy cow. Your confidence interval for the mean is going to be x bar minus z sub alpha over 2 times s over square root of n plus, oops, sorry, not plus, comma, x bar plus z sub, it's not s either, it's sigma. All right. This is if you know the variance. If you know the variance, then you're going to use, obviously, the population standard deviation in your confidence interval. You don't need to calculate it from the sample. It's always going to be a z, regardless of sample size, if you know the variance to start with. Okay? So this is regardless of sample size. Now, of course, in practice, you're probably not going to know the variance ahead of time. It's kind of the point. That's why they call it inferential statistics. You're trying to infer things, not, oh, I already know this. Well, then why the hell are you trying to infer it? Okay? But in some of the problems that you see in the text, if we know the sample, if we already know the variance, then I don't have to worry about t. Okay? I always use z. Okay?
But if we're taking from variable that is not distributed, Should we require the sample size to be big enough?
If we're taking from something that's not normally distributed, then we've got more issues than that for confidence intervals. Yeah, so the confidence interval stuff that we're doing for this is literally for sample means. If we're doing it from a population that's not necessarily normal, then small sample size is really going to throw things off.
Yeah.
Yeah. So,
but if it's big enough, we can still use this, right?
We can still use this, right? If it's big enough, we can still use this because we're doing it for using the sample means to help us get an idea of what the population mean has to be. But if it's small, then even the t distribution is way skewed, which is why we had to use that different form of this, the number of degrees of freedom, that Welch's. Yeah. So if things are really small, things get really screwy. So you have to really widen your confidence intervals. But the way we get the way we end up widening them is just lower the degrees of freedom so that your t values end up being bigger. So then, and if you really have a skewed distribution and you're widening it that much, your confidence interval is pretty much useless anyway. Yeah. At that point.
Also, so when we do this, we kind of make sure that in the tail both are symmetric. Right?
Mm-hmm. Yep.
Is that the reason why they call it two-tailed test or whatever it is? Mm-hmm. Okay.
Yeah, that's why they call it that.
Yep. That was referring to as two-tailed.
Yep. If the variance is unknown, but n is large, we do the same thing. Just we replace the sigma with s. That's an s, even though it looks like a sigma. I'll rewrite it. All right, so now if sigma squared is unknown, n is small, underlying distribution is normal, we use x bar minus z alpha over 2 times, not z alpha over 2, sorry, t of alpha over 2 n minus 1 times s over square root of n. All right. If you can't make the additional assumption that the underlying distribution is normal, then you had to use that weird, funky formula for the number of degrees of freedom, and I'm not going to make you memorize that formula for the test. You've got enough formulas to remember. And that was not intuitive at all. At least these two are symmetric as far as their forms, right? Either I use a z or I use a t. I just have to know, do I get my z value from the normal distribution or do I get it from the t table, whether it's large or small? At least, like I said, at least those forms are actually symmetric with one another. All right. So again, I think I gave you one in the homework where you had to use the weird degrees of freedom, but you won't have one like that on the test because I'm not going to make you memorize that formula. And if I give you the formula and tell you to use the formula, you should know how to plug numbers into said formula. So there's not a lot of point in asking about it. Okay. All right. What else did we do? Differences of means, right? All right, so if sigma squared, x, and y are both known, or both sample sizes are large, we use the difference of your sample means, still use a z sub alpha over 2, and then your standard deviation piece looks a little bit different, right? It's your variance for x divided by the sample size for x. I'll call it m, doesn't really matter. Variance for y, sample size for y. And knowing that you can replace the sigmas with s's if the sample sizes are large, right? And then same thing on the other part. Same thing on the right-hand side. By the way, one thing I didn't mention in class, but I think I might have assigned a problem or two over it. You can also do one-sided confidence intervals, where you're only worried about one side versus the other. If you're doing one-sided confidence intervals, the only thing that changes is that instead of alpha over 2, you would have an alpha on the right, whichever side you're looking for. So if you wanted a lower bound, you would do minus z sub alpha, and then make the right endpoint infinity. Or do a z alpha over 2 on the right one and make the left endpoint infinity. And then you get negative infinity for means. That's how you would do a one-sided interval. You just, instead of having to cut it in half to make it a symmetric interval, you just don't cut it in half and make one side go to positive or negative infinity, depending on how you need it. That's why I didn't go over it. It's not a horribly difficult concept to take care of. All right. 7. Variances unknown but equal. That's important. Sample size small. Distributions normal. I know I haven't been emphasizing it, but in all of these things where we've got either random samples or differences in population means or ratios of variances, which we'll talk about in a minute, you're assuming these things are independent. If they're not independent, you have to do something separate. We'll talk about that more later in the semester. But right now, we're assuming things are independent of each other. Okay? All right, so variance is unknown, but we assume they're equal, and we have small sample sizes, as long as the distributions are normal. So notice that assumptions that we're making, variances are equal, distributions are normal. Okay? Then we use that pooled variance times, or the pooled standard deviation times 1 over m plus 1 over n. Oh, these are not z's, these are t's. I mean, I should tell you what the SP is. we're doing a weight. Essentially, what we're doing is a weighted mean of the variances, right? So you take your Sx squared and weight it with m minus 1 degrees of freedom. You take your S of y variance, your y, the sample y variance, weight it with n minus 1 degrees of freedom, and then divide by the total number.
Here, we're taking x to xm, right, in this case.
Say it again?
Here, we're taking m x variables.
Yeah, m x variables and n y variables. Yeah, now that I'm writing it this way, I think the book does it the other way around. I think they have n x's and m y's. So.
They're also exactly different than this.
Oh, the notes are different. Oh, my bad. Yeah, the thing that's multiplied by the x is number of x's. The thing that's not multiplied by the y's is the number of y's. So I might have it flipped in the notes. For this. Just keep your x's with the x's and the y's with the y's. You'll be okay. That formula looks ugly, but if you remember it's a weighted average, it's not so bad. Right? Essentially, that's why they call it a pooled variance. But again, to be able to use that pooled variance, you have to assume that the variances are equal. Okay? If the variances aren't equal, then you have to do other weird stuff. Move a little faster. Confidence interval for variance. What did we have to do? So we had confidence intervals for variance. So we had to do chi squared of, I always miss them, I always get them backwards. 1 minus alpha over 2, and a chi squared of alpha over 2. Right? And then we had to do something else in the middle. Do I have them flipped again?
Yeah, I think in our notes it's smaller than.
Oh. I always flip them. The smaller number goes on the left, the bigger number goes on the right. That's the thing to remember. I always flip them because it always seems backward in my head. So this one is, let's do this again. Get rid of these. All right, let's try this again. So you're going to use your sample variance definitely. Oh, I know why. I got too happy of writing these things down. I have to divide this by something. This is going to be your chi square of the alpha over 2 on this one. And this is chi square of 1 minus alpha over 2 on this one. And the degrees of freedom are, since I'm using m as the number of x's, I'll use m here. You take your sample variance, it's at both endpoints. You divide by the smaller number on the right and the bigger number on the left, because you want a small to big. You can do one-sided confidence intervals for these too, by the way. But again, you would substitute alpha over 2 with just alpha. Your right end, if you were doing a lower bound, your right endpoint would be infinity. If you were doing an upper bound, your left endpoint would be 0 in this case, because variance can't be negative. So a one-sided interval would have a 0 on the right hand, or the left-hand side. Did I forget my n minus 1 on top? Oh, I did forget my n minus 1 on top. Crap. Thanks. It's a good thing I'm reviewing so I can tell you the wrong things. Yeah, the idea is that, remember this, well, all right, it's an M since I have it that way. This is chi-squared of m minus 1, right? So basically what we're doing is we're exchanging these two for each other because we're trying to get a confidence interval for the sigma squared. We have this chi-squared random variable. I don't know this, but I know this at the 5.05 probability, the 0.95 probability. So I'm just swapping it out. Making it more difficult than it needed to be. My apologies. 9. If we do ratio of variances, so, oh shoot, I forgot. It's minus 1. We lose a degree of freedom because it's variances again. So remember for your F's, you've got a numerator degree of freedom, your denominator degree of freedom, right? So that's where the m minus 1 and n minus 1 are coming from. And when we reciprocate F, it flips numerator and denominator. That's why the degrees of freedom flip on the left-hand side. And then you multiply this by your ratio of your sample variances. And then again, of course, these have to be at the alpha over 2 level. Bless you. Last thing we talked about were confidence intervals for proportions. Right? You might be asked to do something with the sample size. This part here is your margin of error for any of you'll only be asked for margins of error either for means or for populations or proportions, I mean. So this part here is your margin of error piece, if you will. So if you want that margin of error to be, say, 0.05, then you would set that z sub alpha over 2 square root of p times 1 minus p over n. You would set that equal to 0.05 and try to solve for the n. If you needed a sample size to get that margin of error to be that small. Okay? Now, if you've already, I mean, it's goofy. That's why you usually do it the other way. If you already had an estimate for p, you could use that estimate for p to in here, right? But if you don't have an estimate for p, remember what we said? This has a maximum where for what value of p? 0.5, right? So if you want this as your margin of error to be as big as possible, you'll use 0.5 for the p and solve for n. Yes? And when you multiply it together, you get 0.25. Because you take the 0.5 times the 0.5. Yeah. Yeah, 0.25. because it's a half times a half. Yeah, we did say using a point. The 0.25 is actually the product that you'll have on top. All right. So we covered a lot of stuff.
So all we need to know is this. Just
know it, yeah. Just know it all.
We don't have to derive or anything.
No, I'm not too worried about deriving now. I do want to know the relationships between the types of distributions, though, like we talked about at the beginning.
Like this is too.
Mm-hmm.
How long is it?
Mm-hmm. I'm finished with it. Hey, Lee.
When can I take it?
What would you like to take it?
See, that's the thing. I need to know how long it's going to take me because I have no time.
This shouldn't take you more than 2 hours.
That's what you said about probability tests.
I stand by that statement for the probability test, too.
Okay.
I don't think it's as long as probability test. What that?
Okay.
Oh, no.
You tell me.
Can I come in alone on Friday?
Yes.
Like, can you what?
That's fine with me. What's that? You tell me. Yep, you tell me. Anytime tomorrow or Friday.
Let's say like next week sounds good.
Yeah.
Next year.
It has to be by the end of the week. But you tell me. I don't care. On Saturday? I'm not coming in on Saturday, so no problem.
Can I do noon?
Yeah, fine with me. Makes me no difference. I'm happy to do whatever. All right. Holler at me if you got questions.
Yeah.